I'm Bernd Machenschalk and reporting about Einstein at home, a bit more on the technical side here. So as Bruce talked about last week, we have three types of signals we are looking from rotating neutron stars. So basically three search applications for radio waves, gamma rays, and continuous gravitational waves. And we're using analyzing real instrument data that has been pre-processed for better analysis, but nothing more. The radio pulses search is our least demanding application in terms of computing power, memory, and disk space. So this is used for less powerful computing devices like mobiles running Android, Raspberry Pis, PowerPC Macs that we still support, and also smaller Intel GPUs that usually have little memory. The code is publicly available and relatively easy to build. So we also have a few self-built applications on exotic platforms running on anonymous platform. And the challenge with this search is the large variety of platforms, of course. So we have a large variation in runtime. Intel GPU is completing a task in a few minutes, and Android devices struggling to meet the deadline of 2 weeks. And also, of course, permanent issues, cross-platform validation. For the gamma ray and gravitational wave applications, we have separate applications in BOINC terms for computing on CPUs and GPUs because of difference in computing power and as runtime, in memory requirements of the work units. On one hand, memory available on different computing devices on the other hand, and numerical reliability. So for CPUs, we can go with adaptive replication. For GPU results, we rely on complete validation with a fixed quorum of 2. Challenging here is mainly that our gravitational wave apps have a rather short lifespan. So these are updated with new features and a new search every few weeks to a few months. One thing special to Einstein at home is the locality scheduling. We have relatively large amounts of data required even for a single analysis task. On the other hand, we have many work units, dozens to thousands, that are generated per data set, and these data sets overlap. So the solution is to split the data sets into smaller chunks and try to reuse as many chunks as possible on a client side. That's what we developed the Locality Scheduler for. This assigns tasks based on chunks that are already local on the client. So that's where Locality Scheduler comes from. And this minimizes the download volume, both on the client and the server side. As we can't put all of the work units even for one data set into the database, work units are generated on demand. So the client requests work and reports the files it has. The scheduler looks for work in the database that match these files. If there is work found, this is sent to the client. If not, it asks the work unit generator to make more work for this data set, and if that's not possible, for an adjacent one. So the client doesn't have to download a complete new data set. One thing that might be different to other projects on Einstein at Home is server-assigned credit. The runtime of our tasks is pretty deterministic. What these tasks do is match a fixed set of templates to the data. All of these templates take the same time to compute. The number of templates is known in advance and determined by the work unit generator. So the flops and credit per work unit is known and assigned in advance to the work unit by the work unit generator. For CPU applications, we manually adjust the credit per work unit such that the credit per CPU time is constant, at least on average for CPU applications. And when we move work units to computing on the GPUs, we basically keep the credit that we determined from the CPU application. So our rule is that the same science gives the same credit independent of the device that is used to compute it. This makes 5 different main BOINC applications, the radio pulsar one, and for gamma ray and gravitational wave search, a CPU and a GPU one. Currently summing up to 46 different application versions. Try to provide something for everyone. The most recent addition to this is the first native Apple Silicon application, I think in the BOINC project world. We are running 2 schedulers, basically. So the locality scheduler one for the gravitational wave search, the array scheduler for the other ones, which actually is only one scheduler in what we call mixed mode. This means that when a client contacts the scheduler, it gets assigned randomly one of the 2 that tries to fulfill the work request first, and the likelihood of one or the other can be tuned in configuration. Challenge here, of course, is maintenance of such a large pool of applications and application versions, and scheduling. Some things that we stumbled over last year. We are trying to get rid of our old location-based master URL in favor of einsteinathome.org, which is location independent. This is something that is that we still didn't achieve yet. We really don't want to bother our clients or participants with detaching and reattaching or something like that, or annoying them with error messages they don't understand. So we're still trying to test and poke around a bit to circumvent this issues. For a couple of months, we had some performance issues on our upload servers that occurred only on weekends, usually starting at Sunday midnight UTC. That was more or less solved by adding a new server and spreading the load, but yeah, it still leaves us a little bit puzzled. It's definitely not a cron job or something internal that caused that. There was an issue with the Android application that is related to restriction now enforced on new versions of Android, but that was solved. Yeah, and it's one thing is that building applications for older platforms is getting more and more difficult because these are yeah, the build machines that are kept old on purpose can't really run new clients for continuous integration systems or something like that. So that's so we're thinking about dropping support for some old platforms. Yeah, and that's basically it from Einstein at Home.